Hello all. In this session, we learn about how to design a decimal adder circuit. So decimal adder is also one of the example of combinational circuit. In our digital system, so these decimal numbers are represented in the form of binary coded decimal numbers. A BCD adder circuit which can add two digits of BCD and produces a summation which is in the form of BCD, where BCD numbers are valid only from 0 to 9. If your BCD numbers are exceeding 9 or the summation exceeds 9, we have to correct that. So BCD numbers are represented as each digit with 4 binary bits. 5 is represented with 0, 1, 0, 1. 2 is represented with 0, 0, 1, 0. 6 is represented with 4 bits as 0, 1, 1, 0. So to represent 526 of 3-digit decimal number in BCD, we require total number of bits are 4 into 3, which is equal to 12 number of bits. So like this. So we are going to represent the BCD numbers, but when I'm going to add your BCD numbers, we have to check for the BCD summation whether it is less than 9 or greater than 9, or whether it is generating the output carry with a summation of less than 9. So now that 3 cases we're going to see here. With first case, summation is less than 9 with a carry 0. So 6 plus 3 is 9 in decimal, where 6 in BCD is 0, 1, 1, 0. 3 is 0, 0, 1, 1. So now upon using the binary rules of addition, so let we add bit by bit in your BCD. So 0 plus 1 is 1 and with a carry of 0. 1 plus 1 is 0 is the summation with carry 1. So 1 plus 1, 0 is the summation with a carry of 1. So 1 plus 0 is 1, 1 plus 0 is 1. So now as your binary summation is less than 9, which is also equivalent to that BCD summation, so we no need to correct this summation. So since the binary summation is exactly, or the BCD summation is exactly equal to 9. So next case, let me take the summation is greater than 9 with a carry of 0. So we have taken an example 6 plus 8. So 6 plus 8 decimal addition is 14, whereas 14 in BCD is equal to 0, 0, 1, 0, 1, 0, 0. But if I'm doing the addition using a binary adder, we obtain the result as 1, 1, 1, 0. So how to correct this is by adding 6 to this binary summation. So we can correct the BCD summation. 0 plus 0 is 0, 1 plus 1 is 0 with a carry 1. 3 ones with summation is 1 with a carry bit is 1. So now 1 plus 1 plus 0 is summation is 0 with a carry 1. So now so we got the answer, or we have corrected the BCD summation upon adding 6 to that binary summation. So next, so let me take another example which is, or another case. So the third case, which is summation is less than 9 but with a carry of 1. So in order to explain this, we have taken example of 8 plus 9. 8 plus 9 is 17. 17 in BCD is represented as 0, 0, 1, 0, 1, 1. So this we need to obtain. But using the binary adder, upon adding, so we obtain the result is 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0 with a carry of 1. Now first 4-bit addition generates the summation which is less than 9, but it has generated a carry is 1. So in this case also we have to add 6 to that least significant digit addition. So least significant digit summation is 001. Hence add 6 to this and consider that carry as 001 as it is. So now upon adding this 6 to this 4-bit addition summation, or the summation result, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0, and your carry, if with addition of carry, is 0. So now it has been corrected to the BCD summation of 17 as 001, 0, 1, 1, 1. So now, so like this we have to correct that binary summation if your summation exceeds 9. So now first we have to determine. So first we have to proceed with the addition like your ordinary binary addition. So in order to do that, so we prefer the 4-bit parallel adder. Upon adding, if your BCD summation is less than 9, so no need to correct that error. If your BCD summation is greater than 9, we need to add the 6 to that. If it is greater than 9, add 6 to that summation and to obtain your actual result in BCD. So third case is if your summation is less than 9 but carry is generated, there also we have to correct it. So to perform these all the operations, so we require 3 circuits. First one is your 4-bit parallel adder for addition of your given BCD number. Second one, a logic circuit to detect your summation which is greater than 9 or not. Next, third one is, so we have to check for your correction of your binary summation to obtain your result in BCD by adding 6. So now our carry, if it is generated 9 and your summation is less than 9, there also we have to add your 6 to that BCD or binary summation. Now to obtain that logic circuitry, we have taken a truth table where the summation of first binary adder exceeds 9. So from 10 minterm 10 onwards, so we have taken the logical function is 1. So then this correction network output SSOP expression, now it becomes sigma m of 10 comma 11 12 13 14 15. Now upon drawing the k map and mapping your function, then minimizing your expression, we obtain two groups of your adjacent squares. So first group will give you the minimal expression is S3 S2. Second group will give you the minimal expression is S3 S1. So if I am adding, your carry output is also generated. So then C4, your final expression of your correction network is C4 plus S3 S2 S3 S1. So now let me take the block diagram of your BCD adder circuit where I'm going to use for initial addition. So this is the first 4-bit parallel adder which will add your BCD numbers of single digit. So next, in order to correct the summation, we require a correction network. As the correction network output, Y is equal to C4 plus S3 S2 plus S3 S1. So hence we used two AND gates with one OR gate where the inputs comes from your C4 of your first 4-bit parallel adder, and then two product terms, so two AND terms outputs are connected as the input. So that is taken as your output carry, and that has been applied as your the second inputs of your second 4-bit parallel adder. So this first 4-bit parallel adder will add your given binary numbers which are represented in BCD. First case, let I take 6 plus 3. So now 6 plus 3 is 9. So without any carry, our summation is less than 9. So it doesn't generate your the output carry. So hence the result would be like your binary summation, whatever we are getting, that will be equivalent to that of your BCD summation. Now, so given number A is 6, given number B is 3. So binary equivalence of B is 0 0 1 1. Binary equivalent of 6 is 0 1 1 0 on your 4-bit parallel adder, where Cin is 0 for the first 4-bit parallel adder. Now, so here we have a cascaded stages of 4 full adder sessions. So now let I take the first full adder one. Output is based on your inputs of A naught, which is equal to 0, B naught is equal to 1, and C naught, initial carry, C in is equal to 0. So first full adder output is summation output is 0 plus 1 plus 0. Summation output is 1. Carry output C1 is equal to 0. Full adder 2 inputs are B1, A1. So B1 in this case is 1. A1 is 1. Carry input from your previous addition is 0. So our output of summation is 0 with a carry of C2 is 1. full adder 3 is having the inputs of A3, A2, B2, where A2 is 1, B2 is 0. A2 is 1, B2 is 0. Carry output of previous carry is C2 is 1. So C2 is 1. So now summation is 0 with the carry of C3 is equal to 1. Next, FA last full adder in your first 4-bit parallel adder is having the inputs of A3 0, B3 0, C3 is 1, summation is 1, carry output C4 or Cout is equal to 0. So now as your summation of your S4, S3, S2, S1, S0 is 1, 0, 0, 1 with C4 or Cout is 0. Now, so 0, your output function C4 is 0 now. S3 is 1, S2 is 0, S3 is 1, S1 is 0. So hence the correction output is 0. So now that 0 output is transferred as the B inputs of B2, B1 along with B3 is 0 and B0 is also equal to 0 for the second 4-bit parallel adder. Second 4-bit parallel adder A in first inputs are acting like a S3, S2, S1, so which are 1, 0, 0, 1. So 1, 0, 0, 1 with the carry input 1 with the B inputs of 0, 0, 0 generates the summation outputs of second 4-bit parallel adder, which is the BCD summation is equal to 9. So in this case, so we have not have a carry, hence so we don't get your any correction, but whereas another case we have taken as 6 plus 8. So 6 plus 8 is equal to 14 in decimal. Now 6 is your given number B, so which is equal to 0, 0, 1, 1, 0, and given number A is, let us take this as a 1, 0, 0, 0. So now A is 8, B is 6. So in that case, so A is now 8, A3 is 1, A2, A1, A0 are zeros, 8. So B3, B2, B1 are 0, 1, 1, 0. So now first full adder outputs as Cn is 0 here. Full adder outputs are, it will take A0, B0, so 0 plus 0, carry input is 0. So summation output S0 is equal to 0 with the carry input of your carry output of your first full adder C1 is equal to 0. Next full adder 2 output is, so here B2 B1 is 1, A1 is 0, C1 is also 0. So summation is 1, carry output is equal to 0. FA3 is equal to B2 is 1, A2 is 0 and C2 is 0. So output of this S2 value is equal to 1 with C3 value is equal to 0. FA4 last full adder output, if it is having the inputs of B3 is 0, A3 is 1, carry input is 0, summation output is 1 with the carry output of last full adder is 0. Now the S0, S3, S2, S1, S0 outputs are 0, 1, 1, 1. So this is an invalid state in your BCD summation. So hence now let me see the correction network output, which is C4 plus S3, S2 plus S3, S1. C4 as in this case is 0, but S3, S2 are 1, 1, S3, S1 are 1, 1. So 0 plus 1 plus 1, which is a 1 over of 1 is equal to 1. So as since this correction network 1 is 1, so hence we need to add 1, 1, 0, 1, 1, 0 to the summation of first 4-bit parallel adder, which is 1, 1, 0. So this second 4-bit parallel adder will add 1, 1, 0 as taken as a input B input is 0, 1, 1, 0. So upon adding this, so we would obtain the result which is equal to 0 plus 0, summation bit is 0. Next 1 plus 1 is 0 with a summation with a carry of 1. Now third full adder inputs are 1, 1, 1, 3 ones. So hence summation is 1, carry of 1. So 0 plus 1 is 0. So with a carry of 1. So here C out is equal to 1. So like this. So now we obtain from your second 4-bit parallel adder the equivalent BCD summation. So it automatically corrects your result if it exceeds your 9. So using your correction network. So we require a correction network to obtain your actual result from its BCD adder circuit. So this BCD adder requires 2 binary adders along with a correction network. In next class, we are going to learn about another combinational circuit which is a decoder.